Welcome to the abstract video of my research paper, Visual Semantic Context and Map-Based Rotation-Invariant Efficient Estimation of Position and Heading, which is about positioning of an aerial vehicle under GNSS-denied situation. In this case, database reference navigation that compares surrounding features with onboard database is one good remedy, and this study focuses on the ortho-rectified visuals of the ground. However, since the map was built in the past and feature extraction depends heavily on the shooting conditions, naive comparison of aerial images with visual map, such as Google Map, tends to fail. So the basic idea here is to raise the level of comparison up to the semantics, such as buildings and roads, included in an aerial image. Based on our previous research, which trained the neural network how to extract salient semantics out of an aerial image, the problem turns into comparing semantically segmented aerial image and semantics map of the ground. The approach suggested in this study is to further encode semantics image into visual semantic context, or VSC. The principle is simple: gather semantics in polar coordinated fashion and list in azimuthal fashion. We then call this distribution a visual semantic context of the location. Note that the image rotation is equivalent to column shift of a VSC. These are the samples VSCs calculated at different locations. Note they exhibit very different overall trend of the semantic distributions. As an overview of the proposed approach, we first semantically segment given aerial image and extract VSCs. Then compare it with the VSCs calculated on the semantics map, which can be done offline prior to the flight. Then calculate the difference between pairs of VSCs and optimize it to locate where the downlooking images were taken. Since a VSC is considered as a trend of a local semantics or distributions of semantics, we exploit multiple measures of differences between probability density functions, such as L2 measures or Jensen-Shannon divergence, or in short, JSD. Note that the latter one is sensitive to the column shift or rotation of an image. This is a sample residual map with L2 distance is utilized, which is rotation invariant. And these are sample residual maps when Jensen-Shannon divergence is used, provided the true reference locations. This result assumes that heading information is known, and note that such trend comparison exhibit locally unique minimum, even though the tree position is populated with ambiguous and repetitive buildings. This is also a sample residual map represented with respect to heading error. Each 9 figures are taken from the 10 meters mutually distant locations. Based on these two results, one can say that it is easy to find the minimum error of positions given heading information or vice versa. Thus, our approach is twofold. We first coarsely locate position by using rotation-invariant measures such as L2 distance, and then we further refine it via rotation-sensitive measures. Furthermore, the pool of search can be significantly reduced as a VSC is considered as a probability distribution based on a Kuiper hypothesis test, whose null hypothesis is that the two VSCs are samples from the same distribution or same location. One can take a quick look of both VSCs and easily reject a candidates without even calculating the cumbersome JSD or different measures. These are the sample test locations, each of which is assigned respective level of difficulty, such as hard, medium, or easy. Such difficulty was assessed based on local repetitiveness or ambiguity of certain patterns and rotational symmetry. And those repetitiveness and symmetry can be assessed beforehand based on the autocorrelation function given in the figure on the right. For instance, a test site is designated as hard exhibit rotational symmetry so that multiple minimum should arise with respect to heading differences. The resultant autocorrelation has multiple peaks at 90 degrees or the 180 degree rotations. For instance, the H2 case is located among the building forest and is heavily symmetrical. And these are the matching result. The actual comparison target is reduced up to 90% in all non-ambiguous cases, and estimation error is lower than 5 meters in locations and 5 degrees in headings. The ambiguous case, it sometimes fails, yet such case can be predicted beforehand by analyzing the VSTs of the semantics map prior to the flight. So that was the quick summary of our paper. And if you are interested, you can feel free to contact me or the corresponding author. Thank you for listening.